Hi everyone, welcome back to Dave's Math channel. This is my eighth video on my series on number theory, and today I'm going to talk about how you can find very good approximations to square roots, and to particular square roots of non-square positive integers. So let's begin. So how do we do this? Well, the key here is I talked about this a few videos ago. You want to find solution to Pell's equation. It turns out that a solution xy to this Pell's equation, x squared minus ny squared equals 1, will give you a very good rational approximation. Matter of fact, it turns out to be a rational convergent, x over y to the square root of n. Um, it's pretty easy to see that because if x over y is close to the square root of n, then x squared over y squared is close to n. So x squared minus ny squared should be small. In this case, it's 1, which is as small as it can be. Actually, you don't care if it's 1. It could be minus 1. You're just as happy with minus 1. So you might as well try to solve a slightly easier equation, the modified Pell's equation. We're only requiring that, in this case, we call them u and v, u squared minus vy squared is plus or minus 1. And I think you can see that a solution of Pell's equation isn't necessarily a special case of a solution to the modified Pell's equation. So it's enough to solve the modified Pell's equation. And then if you watched my previous video on Pell's equation and the modified Pell's equation, then I think I mentioned the fundamental solution. That's the solution that has the smallest possible values of u and v, or x and y if you like. And we call them u1 and v1, or x1 and y1. And then it's a pretty easy matter to get all the other solutions. It turns out that there's infinitely many. There's always infinitely many solutions to either the Pell's equation or the modified Pell's equation for any non-square integer n. Um, yeah, I think I made a typo on the modified. That should be u squared minus nv squared equals plus or minus 1. But anyway, you get the idea. So that's what we want to do. We want to find these solutions, and that'll give us our rational convergence. And there's a nice algorithm for doing this. And it turns out here's a connection. I've been talking about continued fractions for the last few videos. I think I mentioned when I was talking about Pell's equation that you can use continued fractions to find the fundamental solution to Pell's equation for any value of n. Well, I didn't explain how to do it. Here I am explaining how to do it. So this algorithm will tell you how to do this. It'll give you the first period. It turns out that I think I mentioned that quadratic irrational numbers always have a periodic continued fraction. This is if and only if continued fraction of a real number is periodic or ultimately periodic, if and only if the number x that you're taking the continued fraction of is a quadratic irrational. And in the special case in which x is a square root of a non-square integer, it turns out that not only is the continued fraction periodic, but it has a special form. It's almost completely periodic, not quite. It turns out that the a0, the leading continued fraction coefficient, isn't part of the period. But then you get everything after that is periodic, ending with ak. Ak is the period, and ak turns out to be 2a0. It's always the last term, the last term in the repeating part is always twice the first term, or the 0th term, if you like. And the 0th term is just the integer part of the square root. And so this algorithm tells you how to find these numbers. I'm not going to go through it. It's a little bit complicated, but I'll give you some examples. So anyway, here's a couple simple examples. N equals 2. This is the simplest example, I think. So I'm just following the algorithm here. The algorithm, I might as well go through the algorithm. So first you have to do all this initialization. I think I showed you guys this initialization and the general continued fraction. You always want to initialize or index k to 0, and in this case we're initializing our x0. That's just the number that we're taking the continued fraction of. That's the square root of n. And then in step 2, we're doing more initializations. P minus 2 q minus 2, p minus 1, q minus 1. I think I went over this in a previous video. They're just 0, 1, 1, and 0, respectively. And then we initialize a0 to the integer part of x0, in other words, the integer part of the square root of n. And then what else do we initialize here? Looks like, yeah, the s's and t's. This is new. I'm introducing a couple of new variables here, sk and tk, and I'm just saying s0. So the way you're supposed to think about this, you're going to get a bunch of, remember I had the xk's when I was doing the continued fractions before, or x0 in this case is the square root of n, but we're going to have like xk plus 1 is 1 over square root of um, xk minus ak. It's just the next number you're doing. It's a recursive algorithm, so you keep doing integer parts of real numbers greater than 1. Well, it turns out the real number you're doing, the xk in this case has the form sk plus square root of n over tk, where sk and tk are positive or non-negative integers. So we start with s0 equals 0 when t0 equals 1, because that's just 0 plus the square root of n all over 1, which is just the square root of n. But it's going to give us new xk's of the form sk plus square root of n over tk. And anyway, that's what these numbers mean. And there's recursive formulas for computing further ones. But we start by doing what we did before. These are just the recurrence equations for the pk and qk on lines 4a and 4b. And remember, we're waiting for ak to equal 2a0. When ak is 2a0, that means we're done computing the continued fraction of the square root of n. And we use the same recurrence formula as I gave you last time. pk is ak pk minus 1 plus pk minus 2, and qk is ak qk minus 1 plus qk minus 2. And then our new recurrence equations are sk plus 1 is ak tk minus sk, and tk plus 1 is n minus, what is it? I can't even read this. N minus sk squared over tk. Yeah. So those give us our new values of sk and tk, and then we increase k by 1, and we compute the new continued fraction coefficient, which is just the floor of sk plus square root of n over tk. And we keep going through this loop until ak is equal to 2a0. And when we're done, not only do we get the continued fraction, which is this thing on the left, but we also get pk. It turns out that we get a fundamental solution to the modified Pell's equation as well. It turns out that u1 is pk minus 1 and v1 is qk minus 1. Pretty nice. So this algorithm gives us a lot of useful information. And now I'm gonna give you some examples. So, and like I said, n equals 2 is the simplest example. And I'm just going through the algorithm, all the steps I spelled out earlier. This is just the initialization on top. When k is minus 2, we have p minus 2 is 0, q minus 2 is 1, p minus 1 is 1, q minus 1 is 0. This is always the case. And then when k is 0, we get a0 is the integer part of the square root of 2, which in this case is 1. I put that in red because that's a continued fraction coefficient. I'm going to write the continued fraction of the square root of n in red, which I did here. I should have put lines above the, I should have put a line above the 2 on the right because this is a periodic continued fraction. But anyway, then we still have to keep going through this algorithm. P0 is 1. This using the recurrence formula I gave you, it's a 1 times 1 plus 0, that gives you 1. And similarly, Q1 0 is 1 times 0 plus 1, which is 1. And then our if we apply the recurrence equations I gave you, the SK, AK, and TK, well, we always initialize S0 as 0 and T0 as 1. And it turns out we don't even need S1 and T1. All we need to complete this algorithm is we need a 1, which turns out to be 2, which is indeed twice as big as the first coefficient. So now we're done. Square root of 2 has a continued fraction 1, semicolon 2, which should have had a line above it, because it's really 2 repeating. It's really 1 semicolon 2, 2, 2, 2 ad infinitum. And then you can get the u1 and v1. u1, like I said, was p In this case, k is 1, so it's really just going to be p0, which is 1. And v1 is q0, which is also 1. So our fundamental solution to the modified Pell's equation for n equals 2 is 1 comma 1. And you can check for yourself. 1 squared minus 2 times 1 squared is minus 1. And, it's not very good approximation of the square root of 2, but you can get U2, V2. There's our occurrence formula for getting the bigger solutions, which I talked about in a previous video. And then let's do a little bit more complicated example. N equals 3. Same idea. I don't think I'm going to go through all the steps here. If you calculate the continued fraction of the square root of 3 using this algorithm, you get 1 semicolon, and then you get, I should have had a line above this 1 comma 2. So it's going to be really 1 semicolon 1 2 1 2 1 2 1 2. So it's the 1 and the 2 that are repeating. And it turns out in this case you won the fundamental solution to the modified Pell's equation. In this case is U1 is 2 and V1 is 1. You can check that yourself. U2 in this case is P1, which turns out to be 2, and V1 is 1. And you can check that 2 squared minus 3 times 1 squared is indeed 1. And let's do a more complicated example. These can be as complicated as you want. Here's a fairly complicated one. N equals 19. It turns out for n equals 19, you need a lot of continued fraction coefficients. Here I actually did write the line above the coefficients. But if you apply this algorithm, and I'm not going to go through all the steps, but if you apply the algorithm I showed you earlier, you'll find that the continued fraction of the square root of 19 is 4, and then you get the repeating sequence 2, 1, 3, 1, 2, 8. And if you calculate the fundamental solution to the modified Pell's equation in this case, you're going to get U1 equals 170 and V1 equals 39. And it turns out 170 over 39 is already a very good approximation to the square root of 19. And you can check for yourself that 170 squared minus 19 times 39 squared is 1. In this case, I believe it is plus 1. So one more thing I think I should mention. Whether it's plus or minus 1 depends on the length. It depends on the final value of k. In this case, the final value of k was 6. That's even. So you're going to get plus 1. You always get plus 1 if the last value of k is even, and you get minus 1 if the last value of k is odd. The reason we got minus 1 for n equals 2 was you got a period of 1, which is odd. But we had a period of 2 for n equals 3, so our solution involved plus 1. And the last thing I'm going to mention in this video, like I said, you can get all the other solutions to Pell's equation or the modified Pell's equation once you have the fundamental one. In this case, they even give you the sign. Now, they did this backwards. I don't know why. The Pell's equation is usually yn squared minus 2 times xn squared. So in that case, the first number here would be minus 1 plus 1. The point is they alternate between plus and minus 1. These are the solutions you get. And these give you very, very good these give you rational convergence to the square root of 2. And these numbers have names. These xn's are called Pell numbers, and the yn are called half companion Pell numbers. And it turns out that yn over xn is always a rational conversion of the square root of 2. These get closer and closer to the square root of 2. You can kind of see that from this table on the right. I mean, the first approximation is terrible. It gives you 1. But the next one, when you square it, gives you 2.25, 1.96. They get very, very close. By the time you're already up to the 7th rational conversion, when you square it, you get 2.000006. It's only off by about 1 part in a million. So these get very, very close to the square root of 2 pretty quickly. Pretty nice method. So anyway, that's how you can use continued fractions to compute solutions to Pell's equation or the modified Pell's equation and get rational convergence to the square root of n whenever n is a non-square integer. Pretty nice method. So anyway, that concludes my my talk for today. Thank you for watching. Long live math, and I'll see you guys next time.